Whereas in this chapter we will talk about reactions. Suppose if we have this methyl bromide and you react this one with a nucleophile, that is hydroxide, okay? And then so what will happen, the nucleophile will react with the carbon. Here you see this is carbon has delta positive and bromine delta negative, and then bromine will leave in the form of bromide. So the product here, it will form CH3, that is methanol plus sodium bromide. Okay. So this reaction here, the rate of the reaction depends here the concentration of both the reactants, the base and methyl bromide, the substrate. Okay, this is the nucleophile. Okay. And this is called the substrate. Substrate means the compound that has the carbon that participate in the reaction. So the transition state for this reaction is like this. COH, okay, it forms a bond with the carbon. When it starts forming bond with the carbon, then the carbon-bromine bond starts breaking. And you have here this hydrogen. One hydrogen will be in the back side and one will be in the front. Okay, so this is the structured, you can say the transition state. So when oxygen starts making bond, it will start losing its negative charge, and bromine will start gaining its negative charge. And the charge on the carbon will remain almost constant because one side bond is forming, another side is breaking. So this is the transition state. Okay, so this reaction here, the transition state, say the nucleophile and the electrophile, this is the substrate mix as a complex. So this reaction is called SN2. That means substitution nucleophilic okay, bimolecular. So here rate of the reaction depends on both the molecules, and transition state contains almost both the molecules. Okay, that is the bimolecular, and this is a substitution reaction, and the reaction is started by the nucleophile. So that's why this reaction is called nucleophilic substitution reaction. Now suppose if there is a substrate that is chiral. Okay, so here if you have a bromine and there is a hydrogen, okay, and this is methyl, and you have here ethyl, CH2, CH3. Okay, so what will be the configuration of this one? So it will be 1, 2, 3. So it looks like R, but because the hydrogen at the front, it will be S. Okay, S bromo butane. So this will be called S2 bromo butane. Okay. Now if the nucleophile here, if let's say here KOH, suppose the nucleophile the salt, so it will react here and it will kick off. So the nucleophile will come opposite to the bromine. Okay. So why opposite? See, suppose this is the bond, okay, here, bonding carbon bromine bond. So here opposite side is the anti-bonding, empty, and that is anti-bonding empty. So, and the angle here between these two is 180 degrees. Okay, the bonding between carbon and bromine and anti-bonding is on one plane 180 degrees. So when KOH reacts, so it starts making bond with the anti-bonding empty orbital. Okay, and this starts leaving. So the nucleophile will come exactly from the opposite side of the bromine. Okay. So this will make like this. Okay. So we will have here hydrogen, and this is CH3, and you can write CH2, CH3. So now if you will see the configuration of this is C1, 2, 3. So it looks like S, but hydrogen above it is R. So now it is R2 bromo butane. Okay. So this is so this reaction is SN2 reaction. So one more thing here, few things you need to keep in mind. So the reaction, when we talk about this type of reaction, let's say I will write again OH minus, the nucleophile, and you have carbon, bromine, hydrogen, 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 and then this is the reaction takes place. You need a solvent. Okay. So what happened, this is the first the nucleophile. So if it has the nucleophile means negative charge, so it will be stronger. Okay. And so we'll talk one by one. So first the nucleophile. So nucleophile means that it should have electrons, more electrons. So negative charges will have more electrons. So whenever we talk, suppose if you have a neutral molecule, see here water versus OH minus, the difference is here you have 3 lone pairs, you have 2 lone pairs. So this is a better nucleophile. Better nucleophile. Okay. And another criteria for nucleophile is that the atom should be less electronegative. Less electronegative means then these electrons will be more free, okay, loosely bound, more free, so that will react faster. Okay, so that gives the idea in a periodic table. Okay, suppose here you have the periods, and here you have the group. So in the periodic table, left to right, generally nucleophilicity increases, and in the group from top to bottom, electronegativity decreases, so nucleophilicity increases. So remember the arrows, nucleophilicity. Okay, so for the nucleophile, nucleophilicity will increase in the from left to right and top to bottom. And when we compare for the same atom, then the negative charge will have better will be a better nucleophile than the neutral molecule. Now here comes next is the substrate. Okay, for the substrate, you see here hydrogens, they are small, very small. Okay, if you replace with the carbon, suppose here, okay, here there is a carbon, then what we'll do, the carbons will create a crowd. Okay, So crowd means then the nucleophile cannot approach the electrophilic carbon. So that will make the reaction tough. Okay. So that is the so this is that will make the reaction difficult, and because the nucleophile we cannot increase. So the substrate here, the electrophilic carbon is less structurally hindered, then the SN2 reaction will be easier. So easily you can see that suppose if you have this methyl, okay, bromide, it's a better nucleophile than if you have ethyl bromide, because you are bring one extra carbon CH3. Okay, that is better than isopropyl bromide because it is creating more crowd. Okay, and which is of course much better than the tertiary butyl bromide. Okay, so this is the trend. So less strictly hindered, it will be better, it will react. So remember, for SN2 reaction, the carbon will needs to be sp3 hybridized. Okay, suppose if it is sp2 like this here, bromine if you have, then the nucleophile here cannot approach. Okay, see, the nucleophile needs to approach the carbon. It will not it is not possible to come opposite to the bromine. Okay, because the angle here is 120 degrees, so the opposite it cannot reach in 180 angle, it cannot reach this the double bond carbon. Similarly, if you have a benzene ring and you have a chlorine here, a bromine, so see the anti-bonding for this will be inside the ring, so the nucleophile cannot reach here. So here, so this double bonded carbons that has the bromine, they are the least reactive, or you can say no reaction for SN2 reaction. Okay. So another this type of reaction we have seen in in chapter 10, that whenever we take like I'll give you guys example here. Okay, acetylenic carbon, and if you take this bromomethane, the reaction will happen via SN2 reaction. Okay, so this will form. Okay, so it will be this product. So this reaction we have seen in the previous chapter. So we talked about the nucleophile, we talked about the electrophile, the substrate. Now we need a solvent. Okay, solvent. So solvent is a liquid that dissolves this substrate and the nucleophile. Okay, that is called the solvent. So solvents we can classify like this with solvent polar solvent and non-polar solvent. Okay. So what is polar solvent? That has polarity in the molecules like water. Okay. Water has oxygen has delta negative and this is delta positive. So here you have a dipole, so that is polar. Non-polar, in which the carbon that electronegativity difference is not significant. So the delta this bond is almost non-polar. So example is benzene is a solvent, or cyclohexane is a solvent, hexane is a solvent. heptane is a solvent, and they are the non-polar solvent. In polar, there are two types. So polar protic and polar non-protic, polar aprotic or aprotic. So now in polar protic solvent, I give the example, it means it has a H delta plus in the form like OH, mostly OH, okay? It could be NH as well, okay? So here you have a polar that has the proton H because it can break and it can give a proton like methanol. It's a polar protic solvent. Okay. What is polar protic solvent? Means it is polar but there is no polar H. Like the example is THF. Okay, here oxygen is delta negative, carbon is delta positive, so it is called THF, tetrahydrofuran. Okay, THF. So this is a polar aprotic solvent, and another is DMSO CH3. See, it has a very strong negative charge and positive charge, but there is no delta H. So this is called DMSO, dimethyl sulfoxide, okay? Or DMF. It has that, okay? It's called DMF, and dimethyl formamide, okay? Other examples, there are several other examples, okay? SC2 nitrile is polar aprotic. Here you see that it's a delta negative and delta positive, but there is no H, okay, polar H. So another example of polar aprotic solvent, this is called SC2 nitrile, okay? And another one is called HMPA. Okay, HMPA. So this is called hexamethyl phosphoramide. Okay, so these are the polar aprotic solvent. So for this SN2 reaction, the solvent should be polar aprotic. This one for SN2 reaction. Okay. So here I'll give you guys the example again. So let's say you are reacting sodium hydroxide, okay, plus methyl bromide or iodide. Okay. So this will O reactive H minus will react with the carbon. It will make CH3OH plus sodium iodide. Okay. Here you see this OH minus is not free. Because there is a very strong electrostatic attraction between sodium and hydroxide ion. Strong electrostatic attraction. Okay. So to make free, you need to pull out this sodium. Okay. If you pull it out, then this will be free. That will react. So for this, you need polar aprotic solvent. So suppose if you have like this one, DMSO, okay? Okay? So DMSO, this one. So what will happen, DMSO will come around the sodium ion and the sodium ion will be caged. So it will make it like a cage. It will be caged and the OH minus will be free. Okay, that's why we need a polar aprotic solvent. So if you suppose take so this is a DMSO. If you take suppose a polar solvent like water, okay, so water, what it will do, water will surround the positive ion like this. So delta minus, delta minus, delta minus, delta plus, you will have all, okay, I'm not writing it. So what will happen, sodium will be caged here, and also OH minus will be caged. See, in which the water molecule will be flipped. So delta negative, sorry, positive. So here delta positive, this is delta positive, delta positive, delta positive. Okay. So what will happen? This will make like this cage. Okay. So this one is here, positive charge is caged by the oxygen, and the OH minus both are caged. Do you see here? So that's why the polar protic solvent will not help this one for SN2 reaction. You need a protic solvent. Here you don't have the hydrogen, so it cannot surround the negative charge. Here the positive charge cannot surround because it is too sterically hindered. You have methyl and O minus. Okay, so this is the very important. So the solvent, and so higher the polarity a protic solvent, faster will be the reaction. Another reaction, suppose if you take tertiary butyl, okay, and then you dissolve this one in water, what will happen? It will slowly, it will be hydrolyzed to tertiary butanol. Okay, so what will be the mechanism? So first the mechanism will be that bromine will leave, it will make a carbocation. Okay, as soon as carbocation will form, water molecule will react, and it will make this. And another water molecule will take the proton, and tertiary butanol will form. Okay, so this is the mechanism. So here the rate of the reaction will depend only on the substrate, this one, tertiary butanol. Okay, CH3 twice CBr. So here it is a unimolecular. Rate doesn't depend on this H2O. Why? Because this, as soon as the carbocation will form, immediately it will react. If carbocation will not form, the reaction will not take place. Okay, so very little contribution of this for the for to accelerate the reaction. So here Br is a leaving group. It leaves, leaving group. Okay, so Br, so anything that can leave faster Okay, then the faster will be the formation of carbocation and faster will be the reaction. So for this reaction, the leaving group is very important. In the book you guys can see that table. So this reaction you see, let's talk first the carbocation. Okay, so it is the tertiary carbocation, okay, forms. So when carbocation forms, so it should be stable. Okay, it should be stable carbocation. If it is not stable, then the reaction will be difficult. So if you guys can recall from chapter 7, that carbocations are stabilized by hyperconjugation. So tertiary carbocation is more stable than secondary carbocation. Okay. So the reaction here will be faster than secondary, and secondary carbocation is more stable than a primary carbocation, and primary carbocation is more stable than a methyl carbocation. Okay, so this is the stability. Okay, so here the carbocations are stable because of their hyperconjugation. Hyperconjugation. Okay, so if this hyperconjugation is another form of stability could be that if your carbocations are, see, this resonance stable. Suppose if this is the carbocation, it can be stabilized via resonance. Okay. Similarly, this is called allylic carbocation. Allylic carbocation. Okay. And this is if it is here at the benzylic carbon here, this carbon, suppose. So this will be stable with the benzene ring. So although this carbon is primary, this is primary, but they are stable. It is almost same as the secondary carbocation here. So this will be almost stable as allylic and benzylic carbocations, same like secondary. Okay, because here you see they are primary, but they are stabilized by the resonance, so they are almost same their stability as the secondary carbocation. Now, now let's come to the leaving group. Okay, so see. So the leaving group, as I said, for this reaction, like here, a leaving group, something has to leave. Okay. So OH is the worst leaving group. Okay. OH is the bad leaving group. OH minus. So it's the worst leaving group. Then comes the halogen. Okay. Then comes in the halogen, chlorine is bromine is better leaving group than chlorine, and chlorine is bromine. Then iodine is a better leaving group than bromine, and similarly another iodine is almost same as TOS, tosylate leaving group, TOS, TOS minus, and that is then best leaving group is water. Okay, so we'll talk about this TOS and water. See, suppose if you have tertiary butanol, so here OH is not a good leaving group, okay, because when suppose if it leaves, so it will make OH minus, okay, so that is not a leaving group. It will react back, and so the reaction will go here. But if it gets protonated, suppose with HCl, so then it will be the best leaving group, okay? Plus Cl minus. here it can leave easy quickly. Okay? Then it will form carbocation. And this Cl minus will react here. So it will make this SN. So this is via SN1 reaction. So there are several ways. So OH is not a good leaving group. So we make them as leaving groups by reacting with different substrate. Okay. So one of the ways of making, suppose if you have like this one here. So converting this one into halogen makes a leaving group. So see this reaction, if it takes SOCl2, so this SOCl2, it can react here, it can go here, okay? And also we need a base for this reaction, and pyridine is a base. So it will make CH3, CH2, CH2, OH plus. Okay, here you have it react with the sulfur, O minus Cl and Cl, and pyridine, what it will do? Pyridine will take this proton. Okay, and what will happen? This will come back and this will leave. So it will form CH3, CH2, Cl2, O, S, double bond O, Cl, plus Cl minus, plus here you have pyridine, okay. So this is here as a whole, it's a leaving group, we're leaving. So what will happen? It will go this. So what is the characteristic of a leaving group? Leaving group has so many electronegative atoms. Here you see. Oxygen is electronegative, oxygen is electronegative, sulfur electronegative, chlorine is electronegative. So many electronegative elements it will leave, and here the reaction will take place and the product will be CH2, CH2, Cl. Okay, so this is the example of leaving group. And here the reaction is, this reaction is SN2. See here the carbon is primary, chlorine is a nucleophile. This is a very good leaving group. Okay. So that's how we change to chlorine if OH to make leaving group if we want to do whether SN2 reaction or anything else. Okay. Another similar is called tosyl chloride. Okay, TOS chloride. So what is TOS chloride? So you have sulfur, so this is the structure. Okay? See, sulfur chlorine bond, you have exactly like this. So what will happen? It will react here, this chlorine will leave, and after the proton will leave like this with the help of a base. So this will make CH2, CH2, O, S, S, here you have a toluene. So here you see so many electronegative elements. So this as a whole as a leaving group, and it is called TOS. Okay, so this is a tosyl group. So these are the reactions of SN1 and SN2. In the next part, we'll talk about the